Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson for Chemical Engineering 5220, Intermediate Thermodynamics, we are continuing our study of equilibrium reactions, and we will be looking specifically at activity today. So, species activity is defined as the fugacity of the substance at a whatever temperature, pressure, and molar composition, so in the mixture, divided by the reference fugacity of that species at a pressure of 1 bar and at a reference mole fraction. And by definition, this would be the same as that this is the exponential of the difference between the Gibbs energy at the temperature, pressure, and molar composition and the Gibbs energy of the species in a mixture at the reference pressure and molar composition. All that divided by RT. And we use this because this is how we define our equilibrium constants. Ka is equal to the exponential of negative delta G of reaction over RT, but that also is the product of the AI to the stoichiometric coefficient power for each of our species in a reaction. Now, this table is from Sandler's textbook that summarizes the various ways that we can define these for specific pure substances or mixtures in various phases. And the difference is based on whether or not it's pure or in a mixture, whether it's gas, liquid, or solid, or electrolyte. We also have added that to this list. And then what we consider to be the standard state, the reference. So let's look at a few of these cases more closely. So first, let's look at the activity of a species in a gas. Now that gas could either be pure or a mixture. If it's pure, then the activity is the fugacity of that substance in the gas phase or vapor phase at the temperature and pressure divided by the fugacity of that species in the vapor phase at a temperature and pressure of 1 bar. Now, because we can define a fugacity coefficient, F over P, then this would be the same as saying P times the fugacity coefficient divided by 1 bar. For a mixture, we would look at a particular species and we would instead use in the numerator Fi in a mixture for the gas phase, temperature, pressure, and composition, divided by the fugacity of the pure at temperature with pressure of 1 bar. And so our reference here, our standard state, would be a pure gas at a pressure of 1 bar. Now again, using the fugacity coefficient nomenclature, we could use the fugacity coefficient for the substance in the mixture at the temperature, pressure, and molar composition times the partial pressure, or YIP, and that would be divided by 1 bar. So those are the formal definitions for activity of a gas. On the other hand, many times we are dealing with gases or systems that are at low to moderate pressures. And in that case, the fugacity coefficient is nearly 1, and so we can say that the activity in a pure gas is P over 1 bar, and the activity of a species in a gaseous mixture is the mole fraction times the pressure over 1 bar. Now, what about liquids? For liquids, again, we have the case of pure or a mixture. For pure, this is no problem. We're just going to take the pure fugacity in the liquid at temperature and pressure divided by the fugacity in the liquid at the temperature with a pressure of 1 bar. But in a mixture, we have a variety of standard states, and the three that are commonly used are either a pure liquid reference state, or a 1 molar ideal liquid solution, or a pure liquid that has the properties at infinite dilution. Now, most of the time I think we think of the pure liquid state, and that simply would be the equivalent to what we had for the gases. So it's going to be the fugacity of the species in the mixture in a liquid state at the temperature, pressure, and mole fractions of the liquid, divided by the pure fugacity at temperature and 1 bar. And so that, using activity coefficients, gives me xi times gamma I times the exponential of the molar volume of the gas over RT times P minus the vapor pressure. Now, I have not gone into detail on the 1 molar ideal liquid solution because we won't be needing it for our course, but just be aware that that's another one that you do. And this is why we have the reference molar composition, the xi knots that we showed in the table. Because here you're saying that I have my reference is a 1 mole per liter solution where it's an ideal liquid solution. And so that therefore has a mole fraction, a composition. The third case is where we are looking at infinite dilution properties. So it's a pure liquid, but it's at that tweaky moment right as it's becoming infinitely dilute. And so in that case, it's xi times the gamma I for infinite dilution, exponential of the molar volume at infinite dilution over RT, P minus, and then we'll use 1 bar rather than the vapor pressure because that's our reference state. At low to moderate pressures, for a pure liquid, AI will be 1. But if I have a liquid mixture, it will be xi times gamma I. And that would be for either case 1 or case 3. It's just that the gammas are defined differently. For the pure liquid, gamma I is going to approach 1 as the mole fraction approaches 1. For the infinite dilution, gamma I will approach 1 as xi approaches 0. So those are different. But this case here is the one that we most typically use. Now, what about solids? The definitions are very similar to what we had before. Here, our standard state always would be a pure solid. And so we have these definitions shown here on the screen. So for a pure, you're looking at P minus the saturation or equivalent to vapor pressure, so it would be the sublimation pressure. And in a mixture, you're going to take P minus 1 bar. The interesting thing about this is that at moderate to low pressure, AI for solids, whether it's pure or in a mixture, AI is approximately 1. So we'll use these in upcoming lessons so that we can put these together to evaluate equilibrium, whether we have liquids, solids, or gases, knowing whether or not they are pure or a mixture, and selecting the appropriate standard state. Thank you very much for your time.